Okay, let me stop sharing first so I can see who's here. Okay, so Bartram, I don't see your name. Blair, Donnelly is here. Elwell, I don't see your name. Levingood, I don't see his name. Miller is here. Sheffield is actually here in the classroom. Sullivan is here, and I don't see Tillis's name. All right, so before I start chapter 6, there's one thing I want to mention as far as chapter 5 is concerned. Let me share my screen again. And it was a diagram or a graph that somehow I could not find it when I was teaching from the PowerPoints in chapter 5 from last class. And this goes back to what I was discussing on Tuesday concerning the difference between a real gas and an ideal gas, right? So just to briefly recap that part of it, all the gases that we were dealing with and all the problems that we were dealing with from earlier in this chapter, we are assuming that the gas was an ideal gas, which means that basically it obeys the PV is equal to nRT equation. And basically that comes down to the gas behaving according to the kinetic molecular theory. And we said that real gases do not have two particular properties of ideal gases. One, real gases, they are intermolecular forces that exist between the molecules of the real gas, which is not true for ideal gases. And two, the particle size of real gases is actually non-zero. In the case of ideal gases, we assume that the volume or the size of the particles would be zero, especially when compared to the container that they're in. So that's just basically what we were discussing concerning real gases compared to ideal gases. So the graph that you see here on your screen is a graphical representation of the difference between the ideal gas and a real gas. Now, in this particular case, what we're doing is plotting on the y-axis PV over RT, and on the x-axis we have P, right? And we're assuming that because PV, whoops, okay, this is not right. Because the ideal gas equation is PV is equal to nRT, right? That means that N is equal to PV over RT. And we're assuming for the purposes of this particular graph that N is equal to 1 mole, all right? So we're dealing with a 1 mole of gas in a container. Doesn't matter what the pressure is or the volume is. All we know is, or the temperature for that matter, all we know, what's that sound? Oh, okay. So basically, all we know is that PV over RT is equal to 1 mole, right? So this dotted line here shows you basically the plot for an ideal gas, right? As you see here, the pressure changes, which means that the other variables will change such that in this equation, it becomes equal to 1 mole, right? So that's basically what the dotted line here represents, right? Now, the other lines or the other curves that you see here are actually for real gases at different temperatures, all right? So this green line here is the plot for real gas, PV over RT versus P, when the temperature is 200 degrees, or I should say 200 Kelvin. And then for the red line here, the temperature is 500 Kelvin. And then for this line, which I think is blue colored, the temperature is 1000 Kelvin, right? And what do we notice is that as the temperature increases from 200K to 500K to 1000K, you see that the curve becomes more flattened. In other words, it approaches the more ideal particular, the ideal gas situation, right? So in this case here, this is the curve for the 200K, and then for the 500K, the curve kind of flattens out, all right? And then for the 1000K, flattens out even more. And as you can imagine, if you continue to increase the temperature, then basically the plot will be basically the same as the ideal plot. So what does that mean? How do we interpret this physically? Well, what this means is that as you increase the temperature of the gas becomes more ideal. And if you think back to the kinetic molecular theory, that makes sense. Because as you increase the temperature of the gas, you're imparting more energy to the gas particles, and therefore the gas particles will be able to act more independently of each other, and therefore the intermolecular forces will be reduced, and therefore, as a result, the gas particles or the gas itself will become more and more ideal, all right? And this basically goes back to something we said where we talked about, and I think I can bring it up here. I talked about the fact that, let me see if I can find it here. When it comes to temperature, basically, if the temperature is low, then the gas will not be approaching the ideal, it will be less and less ideal. So therefore, conversely, if you increase the temperature, that means that the gas becomes more and more ideal, all right? So that's basically the missing thing that I didn't get to talk about in the last class, and that's why I'm covering that right now, this particular graph, all right? Okay, so that's that. So now we're gonna move on to chapter 6. And in chapter 6, the topic is thermochemistry. So what is thermochemistry? Well, thermochemistry is basically that area of chemistry which deals with energy changes in a chemical reaction, all right? So that's what we'll be talking about in this chapter. Here are some terms that I need to introduce or reintroduce to you guys so that we can get a firm foundation before we move on to more complex stuff. And the first of these terms would be this term energy. And simply put, energy is the capacity to do work. What do we mean by work? Well, work is said to be done when force is applied to an object and the object moves, all right? So if you apply force to an object and the object moves, then work is said to be done. If you apply force to an object and the object does not move, then basically work is not done, all right? So that's what energy is. Energy is the capacity to do work, all right? Now, I don't remember if it's Greek or Latin, but the term energy literally means work within, from whatever the original language was, right? However, technically speaking, an object does not contain work. Now, an object can do work, and as a result, if an object does work, then it loses energy, or if work is done on an object, then it gains energy, and we'll talk about that shortly. Now, most forms of energy can fall into one of two categories. You have one type of energy, which is known as potential energy, which is the energy an object has by virtue of its position or composition. And then you have kinetic energy, which is the energy an object has by virtue of its motion, all right? Now, there's a formula that is used universally to calculate the kinetic energy of a moving object, and it is this formula right here. Kinetic energy is equal to half mv squared, where m is the mass of the object in kilograms, and v is the speed of the object in meters per second, right? So if this, right is here, if m is in kilograms and v is in meters per second, which would be squared because the velocity is squared, then basically the units of energy would be kilogram meters squared over second squared. And the name given to that collection of unit, it's called a joule unit. So whenever you see the joule, it's the same thing as this collection of units right there, kilogram meters squared over second squared, right? And that's the metric unit or the SI unit for energy, all right? Some other terms that you will need to know for this particular chapter. Well, we talked about what thermochemistry is already, but there are other terms as well. So whenever you hear the term system used in this context, right? Basically, we're talking about the part of the universe being studied. And that could be literally any part of the universe, all right? So for example, it could be a beaker, it could be a test tube, it could be a room, it could be anything, right? Whatever we're focusing on in terms of looking at the type of changes that are occurring within that part of the universe, right? And then the surroundings would be the rest of the universe, right? And basically in thermochemistry, we're looking at the energy changes that takes place in the system and in relation to how that affects the rest of the universe, right? Now, when it comes to different types of systems, there are three types. You have the open system, the closed system, and then the third type is called the isolated system, right? And of course, the differences are outlined right here. In the case of an open system, you can have the exchange of energy and matter between the system and the surroundings. In the case of a closed system, energy can be exchanged, but not matter. And then in the case of an isolated system, you cannot have any exchange of matter or energy between that system and its surroundings, all right? So that's the difference between these types of systems. Open, you can have exchange of energy between the system and surroundings. In a closed system, only energy can be exchanged, but not the matter itself or the material. And then isolated system, you can have neither energy or matter being exchanged between the system and surroundings, all right? So this bottle of honey here that you see here, that is a closed system, right? Because it's sealed, you will not have matter being exchanged between that system and the surroundings, but of course you can have energy changes as far as the system is concerned. So therefore you can, for example, warm up this bottle here, and that would mean that energy would be transferred from the surroundings to the system, all right? And that is basically what this diagram is showing right here, all right? Now, excuse me, a question is being asked here in this green box. It says, after the lid of the jar is unscrewed, what kind of system is it? And the answer is obvious. It would be an open system, because now you can have an exchange of energy and matter between the system and surroundings, all right? Okay, so that's also, these are some terms that you need to be aware of in this chapter. Another term I need to introduce to you is this concept of internal energy, which is basically the total energy that is contained within a system. Now, this energy has several parts to it. Some of it is kinetic, some of it is potential, and we talked about the difference between those two. In terms of kinetic energy, now, just to remind you, kinetic energy is the energy an object has by virtue of its motion, right? And in the case of chemical systems, which basically contain substances which can exist as molecules or ions or whatever, these are the different types of energy which would together collectively make up kinetic energy. You have what is known as translational energy or translational motion, where basically the object is moving in straight lines. You can have rotational motion, where, for example, you can have a molecule rotating about a particular axis. And then you have vibrational motion, which is being demonstrated here, where if you have two atoms connected by a bond, they basically vibrate around a central mean position, all right? So collectively, these energies are also called thermal energy, because it turns out that the temperature of a system is related to the kinetic energy that is displayed by the particles within the system, all right? Another part of internal energy is potential energy, and these are basically as a result of intermolecular and intramolecular forces of attraction due to the location of atoms and the bonds, which are made up of pairs of electrons shared between atoms, all right? So collectively, these energies are called chemical energy, all right? So that's basically the difference between potential energy, or I should say internal energy. Well, what internal energy is, and the fact that part of it is kinetic and the other part is potential. Okay, then we have another term here, heat, which is oftentimes symbolized by the letter U. And by the way, let me go back here. The internal energy symbol is U, uppercase U, that is traditionally the symbol that is used. In some textbooks, you'll see they use E as well. All right, so don't be surprised if you look in some textbooks and you see E being used, it's the same thing. And then Q is used to represent heat. Now, heat oftentimes is referred to as a form of energy, but strictly speaking, what heat is basically the energy transfer that occurs between a system and surroundings, which is caused by a difference in temperature, right? So basically, if you have two objects of different temperatures and they're somehow connected to each other, then basically what will happen is that you're going to have the heat flow from the warmer object to the cooler object. So that heat transfer, or that transfer of energy, is what we call heat, all right? So here is a hypothetical example demonstrating the whole concept of heat. Let's say you have argon here on this side of this hypothetical thin wall, and you have nitrogen here on the other side. The argon are more energetic compared to the nitrogen. So therefore, when they bounce off the wall here, the energy is transferred to the nitrogen, right? and therefore the energy that is transferred from the argon to the nitrogen is in the form of heat. And this energy transfer will continue until you reach a state which is known as a state of thermal equilibrium. And what does that mean? Basically, what that means is that the heat transfer will continue until the temperatures of the two substances, in this case, argon on one side, nitrogen on the other side, the temperature of those two gases are the same. Once the temperature reaches the same, right? In other words, the temperature of the nitrogen would increase, the temperature of the argon will fall until they're at the same level. Then basically there'll be no more transfer of heat, all right? So that's basically what we mean by thermal equilibrium, all right? And this concept will become important later on when it comes to certain problem-solving exercises. But before we get to that, let's look at this question. It says, how does the root mean squared speeds of argon atoms and the nitrogen molecules compare at the point of thermal equilibrium? All right, now, just to remind you, in fact, I think I'm going to need some space here, so let me get out of this here. Whoops, didn't need to do that. Meant to do that. Okay, so let me go to here, and let me get rid of this. So just to remind you, the formula for root mean squared speed is, let me do this here. The formula for root mean squared speed is, as you should recall from chapter 5, is equal to the square root of 3RT over M, all right? So that's the formula for the square root mean, the root mean squared speed, right? So the root mean squared speed for argon will be given by square root of 3RT over M. And the root mean squared speed for, what was the other guess? Nitrogen is equal to, oh, by the way, this should be the molar mass of argon right here, and a similar equation where this is the molar mass of nitrogen, all right? So what the question is asking is, how does these two compare? How does this compare to this? Well, what we could do is something kind of similar to Graham's law, where we compare the root mean squared speed of argon to that of the root mean squared speed of nitrogen. And that would be equal to the square root of the molar mass of nitrogen divided by the molar mass of argon, all right? So the molar mass of nitrogen would be 28.02 grams per mole. And the molar mass of argon is, what's argon? The molar mass of argon is 39.95 grams per mole. 39.95 grams per mole. So basically, we have to do the calculations for this. So it will be 28.02 divided by 39.95, and then I find the square root of that. So according to my calculation, this works out to be equal to 0.8375. Right? So that's the root mean squared speed of argon divided by the root mean squared speed of nitrogen. So basically, that's a ratio, right? In terms of the comparison between argon and nitrogen in terms of the root mean squared speeds, all right? Okay, so much for that. That's an answer to this question right here. All right, so continuing our discussion, another term which I alluded to earlier, work, right? As I said before, work is basically what happens when you apply force to an object and the object moves a certain distance, right? And basically, like heat, work is a form of energy transfer between the system and its surroundings, right? Now, if you are talking about a system that has, in its process or in its change, resulted in a negative quantity of work, or a negative quantity of work was applied to the system, basically what that means is that the system loses energy. And what that means basically is that the system is doing work on the surroundings, all right? The positive would be the opposite. In other words, if a positive quantity of work is applied to an object, that means that the object will gain energy, which means basically that the system or the object will be gaining energy from the surroundings, all right? So that's basically what we're talking about when it comes to work. So key thing you need to remember is that there's no such thing as a negative work or negative energy. Or I should say, I take that back. There is something as negative work. There's no such thing as negative energy per se or positive energy. The sign basically indicates the direction of energy flow. So basically, if energy is absorbed by a system, then the sign would be positive. But if energy is lost by the system, then the sign would be negative. All right. So just to give you a kind of hypothetical application of what we just talked about, let's say we have this system here where we have a gas trapped in this vessel right here, and we're going to assume a lot of things for simplicity's sake. For example, we're going to assume that basically the gas cannot escape through the corners here, and this plate here is movable and it's frictionless when it moves. All right. So just to make things a bit simple, those are the assumptions that we're going to make, right? So basically, if the gas expands from here to here, right? So in other words, the final volume would be equal to the initial volume. Then we can calculate the work that is done on the gas using this formula here. Work is equal to minus P times delta V, right? P is the pressure that is exerted, and delta V would be the change in the volume, all right? So basically, in this particular case, going from here to here, delta V will be positive because the final volume would be greater than the initial volume. So let me just put here, in this particular case, delta V is positive, right? And if delta V is positive, that means that W will be negative because of this negative sign right here. And the fact that W is negative, that means that the system is doing work on the surroundings. All right. And if the system is doing work on the surroundings, that means that the system, let me say, therefore, the system is losing energy. All right. So that's basically what happens when the gas is expanding. All right. Okay. We call this pressure volume work, by the way. The W here, we call it pressure volume work because of the formula that is used to calculate it. W is equal to minus P times delta V. All right. Okay. So let's move on now to another term which we need to talk about. And that term is what we call the state function, right? So whenever we're talking about the state of a system, right, we're talking about its exact condition at a fixed instant. Now, let me just say that you are probably, well, not you're probably, you're most likely familiar with the term state referring to the different states of matter, solid, liquid, and gas, right? Well, it turns out, strictly speaking, that the term state actually means something a bit more, more than just that, right? As stated here, the state of a system is the exact condition at a particular instant, all right? So as stated here, the state is determined by different things, the kinds and amounts of the matter present, the structure of this matter, the molecular level, and the prevailing temperature and pressure. So let me give you an example. And let me go back to my writing application here. So let's say you have a piece of iron, which of course, under normal circumstances, is solid. And let's say the initial temperature is 25 degrees Celsius. And if you were to heat that iron to, let's say, 50 degrees Celsius, believe it or not, this iron here at 50 degrees is in a different state compared to this iron here at 25 degrees. Even though in both states, it's a solid state, but simply by virtue of the fact that the temperature changes, that means that the state is different, right? Or let me give another example. Let's say you have hydrogen gas, which is a gas, and let's say the pressure is 1 atmosphere initially, and let's say that you cause it to change such that the pressure is reduced to 0.5 atmospheres, all right? Again, this is a change in state, just by virtue of the fact that the pressure changes, right? Even though you start off with hydrogen gas and you end up with hydrogen gas, it's in a different state because the pressure changes. So if things like the state, the temperature, the amount, and all of that changes, that corresponds to a change in state, all right? So that's what we mean by state, all right? So going back to the PowerPoint here. So let's talk about what we mean by a state function. A state function is basically a quantitative property that has a unique value that depends only on the present state of the system and does not depend on how the state is reached. In other words, it does not depend on the history of the system, right? So basically, there are several state functions which fits this definition here. And one of them we're going to look at is what is known as enthalpy. But temperature is a state function, pressure is a state function. So anything that depends on the state of the system, that is called, any quantity I should say, that is dependent on the state of the system, that is called a state function. Okay, let me also introduce to you this law, which you should have met in introductory chemistry or high school chemistry, and will play an important part in this particular chapter. It's called the law of conservation of energy, also known as the first law of thermodynamics. And basically what this law says is that in a physical or chemical change, energy can be exchanged between a system and its surroundings, but no energy can be created or destroyed, all right? So that's the first law of thermodynamics. And you'll see this expressed actually in different ways. In fact, another way of stating it more succinctly is that energy cannot be created or destroyed, all right? And I should add, in any physical or chemical reaction. So the inference that we can draw from this particular law is that the internal energy change of a system is simply the difference between the energy between, simply the difference in energy between its final and initial states. In other words, the change in internal energy, that's what this represents, is equal to the final internal energy value minus the initial internal energy value, all right? So that's basically what we can conclude from the first law of thermodynamics. Now, as far as that is concerned, we can also come to another conclusion, and that is if energy change occurs only as heat and or work, then the relationship between the change in internal energy and heat and work is given by this equation here. Delta U, the change in internal energy, is equal to Q plus W, all right? So that's a consequence also of the first law of thermodynamics. All right, so at this juncture, I want to talk to you about the use of this equation, and more specifically, the sign convention that would come into play when you're using this equation, right? So the first thing I want to mention here is that when energy is entering any system, then the change overall for that system is going to be positive, right? Because the system is absorbing energy, so therefore its energy will increase, right? Now, there are two ways this can be done. Either by the system absorbing heat or work is done on the system. So if the system is absorbing heat or if the surroundings is doing work on the system, then basically energy will be entering the system, and therefore the consequence of that would be that the internal energy of the system will, the change will be positive, right? On the other hand, if energy is leaving the system, that means that the system would undergo a negative change in internal energy, and that can be done by two ways. Either heat given off by the system or work is done by the system, all right? So whenever you're using the first law, or more specifically the equation I just showed you, delta U is equal to Q plus W, you need to pay attention to the sign, especially when it comes to the questions being worded a certain way. You have to basically read the question carefully so that you know how to use the appropriate signs in that equation. And I think the next slide is an example of that. Yes, indeed. So this question says a gas. Now notice how this question is worded. I want to highlight how this question is worded, right? The question says a gas does 135 joules of work, right? While expanding. And at the same time, it absorbs 156 joules of heat, all right? So pay attention to how the question is worded. The gas is doing 135 joules of work. So that means that W is W positive or negative? Anybody? If the gas is doing 135 joules of work, that means that the gas is doing work against the surroundings. Would you say that W is positive or negative? What's that? Nope. If it is doing work, it's losing energy, right? So therefore, W would be minus 135 joules, right? And then now it says, at the same time, it absorbs 156 joules of heat. So what does that say about Q, the heat? Is it positive or negative? Exactly. So it's going to be positive 156 joules, right? So therefore, when you're calculating delta U, which is equal to Q plus W, Q is equal to positive 156 joules. And then you're going to add that to negative 135 joules. So whatever that gives, that would be the answer. So 156, 156 minus 135. So according to my calculation, this works out to be equal to 21 joules. So therefore, the change in internal energy will be positive overall for this gas. All right. So this underscores the importance of reading the question carefully so that you know what the sign would be for W and Q, and then you can just plug those numbers into that equation. While we're at it, let me give you assignment number 6. And for those of you out there in Zoom, I think I may have published that assignment. Let me make sure. Let me go here, let me go here. And then let me go assignments. Oh, okay. So let me publish it now. I thought I published it earlier, but I guess not. Okay, let me just say for you folks out there in Zoom, I have 2 links. One is chapter 6, and then one is chapter 6 addendum, right? So basically what you need to do is print both of them and then staple them together because it's just one assignment. And for you here, I already did that, so. All right. Okay, so the reason why I want to give you this assignment now, because question 1 is very similar to what we just did. So let me upload, or I should say download, assignment 6 right here. Okay, so again, it's very important that you read the question carefully so that you know what signs to apply. The question says, calculate the total change in internal energy. Now here they use delta E, delta U is the same thing, all right? So don't be confused about that. Of a system when 400 joules of heat is applied to expanding oxygen and the gas does 350 joules of energy. So let me just highlight, hold on 1 minute. Let me just highlight the important terms. So here it says when 400 joules of heat is applied. So what does that tell you about heat in this case? Q is equal to what? Now think about it. It's applied to the system. 400 joules of heat is applied. So that means that the system is absorbing the heat. So therefore, that means that Q is positive 400 joules, right? And then in the case of the 350 joules of work done on its surrounding, what that means is that work is what? Minus 350 joules. Okay. So therefore, delta U or delta E would be 400 joules minus 350 joules equals to 50 joules. All right. Okay. So that's basically how that question is done. All right. Now for question number 2, this is based on an equation which I showed you earlier. Let me clear this and let me scroll down. So the question says calculate the energy in joules, calories, and kilojoules of a particle. It gives you the mass and it gives you the speed, right? Okay, so what equation would you use to solve this problem? I gave you that equation earlier in the PowerPoint. EK is equal to 1/2 mv squared, right? So half of the mass. Now the mass is right here, right? 9.11 times 10 to the minus 28 grams. But remember I said that the mass must be expressed in kilograms. So that means we have to convert this from grams to kilograms. And 1 kilogram would go up top here. 1,000 grams would go below here. And then we multiply that by the velocity squared. The velocity is given as 6.00 times 10 to the 5 meters per second. So we squared that. And that's basically it, right? So let me do that calculation. So that's 0.5 times 9.11 times 10 to the minus 28. And then divide by 1,000. And then I multiply by 6 times 10 to the 5 squared. So according to my calculations, this works out to be equal to how many sig figs? Okay, 3 sig figs. So 1.64 times 10 to the minus 19, and the units would be joules, right? So we have answered this part, but the question is also asking for the energy in calories. So how would we convert from joules to calories? What do we multiply this by? Anybody? And that includes you guys out there in Zoom. Feel free to chime in. Actually, well, it depends on what you're using. Let me write this down. The conversion between joules and calories is 4.18 joules is equal to 1 calorie. All right. So what goes where? 4.18 joules below and 1 calorie above. And that would be what? Okay, so according to my calculation, 3.92 times 10 to the minus 20 calories, all right? Now they also, so we have answered this part. They also ask for the kilojoules, so that's easy because I'm just going to put 1.64 times 10 to the, oh, this should be minus 19, by the way. And this should be, hold on, maybe that changes things a bit. Let me see here. 1.64 times 10 to the minus 19 divided by 4.18. Okay, so this should be minus 20. And then here, 10 to the minus 19 joules. Basically, we're going to multiply by 1 kilojoule above, 1,000 joules below. So basically what that comes down to is dividing by 1,000. And the answer I got is no, hold on, wrong thing. What am I doing? 1.64 times 10 to the minus 19 divided by 1,000. So that would be 1.64. 1.64 times 10 to the minus 22 kilojoules, all right? And that's it. So that's how you do those questions. Okay, any questions about any of these? Any questions? Any questions? Okay, let me clear these, close that out. Let me go back to the PowerPoint. If I can find it right here. Okay, so let me go full screen and then next slide. All right, so now we're going to talk about heats of reaction, and this is where we're going to see the connection between what we have been discussing in terms of energy changes and all that good stuff and chemical reactions, all right? So let's talk about heats of reaction. And okay, what's going on here? Okay, so when we're talking about the heat of reaction, which is symbolized by Q reaction right here, it is the amount of heat that is exchanged between a reaction system and the surroundings. Now, in this regard, there are two types of reaction when it comes to these observations. The first type is what we call exothermic reaction. And these are reactions that basically produce heat, right? So basically, what will happen if it's an isolated system, the temperature would increase because the system is generating, or the reaction is generating heat, right? And therefore, as a result of the reaction is generating heat, the system itself will go from a higher state in terms of energy to a lower energy state, right? So what does that mean? That means that the heat of reaction, co-reaction, is negative, all right? So basically, if a system is giving off heat, its energy state will change such that the energy of the products will be less than the energy of the reactants, and therefore Q reaction is negative. On the other hand, if the reaction is endothermic, then the reaction will absorb heat, and therefore what we said about exothermic, the opposite will be true for endothermic reactions. In other words, in an isolated system, the temperature would decrease, and the system will move from a lower to a higher energy stage, right? In other words, Q reaction will be positive. So there are a couple of examples, and I probably should have brought some demonstrations here to explain this difference. If you take, for example, sodium hydroxide, and you add it to water, and you stir it, make sure that the sodium hydroxide dissolves, and you feel the outside of it, right? It's going to feel warm or even hot, depending on how much sodium hydroxide you add to it, right? That's because when the sodium hydroxide dissolves in water, that process is an exothermic process, all right? Because it generates heat, and therefore it's going to feel hot, and that's why it's hot to the touch when you touch the outside of, let's say, the test tube. On the other hand, endothermic. Okay, an example of an endothermic process would be if you dissolve ammonium nitrate in water, right? So let's say you have a test tube with water, you add ammonium nitrate to it, you feel the outside, it's going to feel cool or cold, again, depending on how much you have added to it, right? That would be an endothermic process because it feels cold. So what that means is that it's absorbing heat from your hand when you touch the outside of the test tube. So therefore, that's endothermic, right? So that's the difference between an exothermic and an endothermic process or reaction. Now, this diagram here basically, again, demonstrates the type of things that occur, in this case, in an exothermic reaction. And if you understand this, then you should be able to basically explain what would happen in the case of an endothermic process, right? Now, in all of these situations, the surroundings have a temperature of 25 degrees Celsius, right? So in the case of the first hypothetical situation where, and this is purely hypothetical, will not happen in reality, but just to explain what will happen. Let's say that the reaction is taking place here, and the reaction, as we said before, is exothermic, so it generates heat, right? And let's say that all the heat that is generated escapes to the surrounding. Very rarely happens. In fact, I can't think of any situation where that would happen, but let's say that happens. If that happens, then what will happen is that the temperature of the system itself will remain the same at 25 degrees, all right? So that's what happens in this hypothetical system. Now, what is more likely to happen in reality is that some of the heat will be escaping into the surroundings, but the rest of the heat would be used to increase the temperature of whatever is left inside here. So you'll notice that the temperature here would be 32.2 degrees Celsius, even though the surroundings is 25. And that's because some of the heat that is generated will escape to the surroundings, but the rest of it will be absorbed by the solution. So therefore the temperature will rise to about 32.2 degrees Celsius. Now, what we can do, and this is basically what happens when you're actually measuring heat change in the reaction, is that instead of doing the reaction in a normal beaker like this, we do it in a system which is totally insulated, right? In other words, this is an isolated system, right? When that happens, there'll be no heat escaping to the surroundings. So therefore, whatever heat is generated will warm up the solution that is remaining in the system right here. And what will happen is that the temperature will increase to a higher temperature compared to what happened in this particular case, right? So this is basically used more often. This sort of setup is used more often in an experimental case where you want to find out how much heat is generated, or conversely, how much heat is absorbed in an endothermic reaction, so that you can do certain calculations with it, all right? Okay, so that's what happens when you compare the temperature change that will occur in an exothermic reaction in these three systems. And as I said before, if you understand this, then you should be able to predict what will happen in the case of an endothermic reaction. In each of these cases, I'm going to leave that for you guys to figure out. But if you have any questions, of course, please feel free to ask me. All right. Okay. So now we're going to look at some changes when it comes to the internal energy in different situations. We're going to look at changes in internal energy when the volume is constant, and then changes in internal energy when the pressure is constant. Now, we're going to come back to this equation right here that we were introduced to earlier. Delta U is equal to Q plus W, right? Now, remember, we said that W, use a different ink. Whoops, sorry. Why is this happening? I'm sorry about this, folks. Let me try this again. All right, you know what? Let me use this. Okay. All right, you know what? Let me continue. So we're going to look at what happens in the case of a change in volume. In fact, let me just do all this here. Okay. So if there's no change in volume, I should say, if the volume is constant. Now, let me remind you that, okay, let me do this, that the equation for work is, let me squeeze it up here. Work is equal to minus P delta V, right? Now, if delta V is equal to 0, that means that work is equal to 0. And if delta U is equal to Q plus W, that means that when delta V is equal to 0, work is equal to 0. That means that this drops out. So therefore, you're going to end up with delta U is equal to simply Q. And we use QV basically to indicate that the volume is constant. All right. So basically what this is telling us, that if we have a situation where you have a reaction taking place, but there's no volume change, that means that all the thermal energy that is produced, let's say it's an exothermic reaction, will be released as heat, right? And therefore there'll be no work being done, no PV work will be done in that sort of situation. Now, let me just say that this, in reality, in the vast majority of cases where it comes to chemical reactions, will not happen, because it's very unlikely that you'll have a situation that can be done unless you set up the experiment for this purpose, where the volume is held fixed, all right? So it's a nice theoretical thing to look at, very interesting to look at, but in reality, this is not likely to occur. What is more likely to occur, going back to this here, what is more likely to occur, and let me get rid of this here while I'm at it. Okay, so what is more likely to occur is where the reaction is operating or being conducted under conditions of constant pressure. Now, in that particular case, delta U, let me rewrite the equation that I had before. This thing is not. Okay, can you guys hear me? Let me know. Can you hear me? Okay, good. All right, thank you. I don't know what happened. I lost you guys for a moment. Okay, so let me go back to this. I don't know how much of it I went past that you missed, but I'm going to assume that you were there for the discussion on the previous slide. So let me just restart this one right here. So what I'm talking about here is where there's a change in internal energy when the pressure is constant. And I was saying that in this particular case, going back to this equation, delta U is equal to Q plus W, right? That means that when the pressure is constant, Q becomes QP, and W, remember we said is equal to minus P delta V. So that goes here. So therefore we can rearrange this equation to get delta U plus P delta V is equal to QP, right? So this is more likely what can be done if you do any chemical reaction under normal conditions. It will be done under conditions where the pressure is constant, right? So how do we interpret this? Basically, based on this equation, we can come to the conclusion that most of the thermal energy would be released as heat, right? Assuming that the reaction is exothermic. But some of the energy is used to expand against the surroundings, right? Which would be the P delta V part of this right here, all right? So that's basically what is more likely to be the case when it comes to chemical reactions being done under normal conditions, all right? Now, enthalpy, let me define this term right here. Enthalpy is the sum total of the internal energy and the pressure volume product, right? And the pressure that is measured, or I should say the enthalpy that is, the heat that is measured under constant pressure, we call that the change in enthalpy, right? Because of course, when you have a heat change, the internal energy is going to change and work will be either done on the system or by the system, which is given by this part of the equation. And this here is the same thing as delta H based on this equation right here, right? Because delta H would be equal to delta U plus P delta V, where P is constant, all right? So just to give you an example, a real chemistry example, we have a reaction here where magnesium is added to hydrochloric acid, and hydrogen is one of the products, a gas that is produced. And let me go here. And basically the gas that is produced will be pushed out against the surroundings, right? And that is basically what happens as far as this part of the heat change is occurring. The delta U part is basically the change in internal energy of the entire system, right? And QP will be the enthalpy change, which in the case of this reaction would be negative, all right? Because the reaction is actually exothermic. So as stated here, the hydrogen that is produced pushes back against the atmosphere, so therefore work is being done, right? So as stated here also, which is what I said before, oh shoot. Okay, so I guess this is not, I forgot to share my screen, folks. Sorry about that. I'm really messing up today. Okay, I'm sorry about that, folks. So let me just back up a bit. So I was just saying here, let me go back to, okay, so let me just go back to this slide right here. I'm sorry about that. So as I was saying here, this is the equation here for constant pressure conditions, right? And I was saying that this equation here is the equation that is used to measure the heat change under such conditions. And that is derived from a combination of this equation here and this equation right here, which we met before. All I did was put minus P delta V where W is, and you end up with this equation. And then I rearranged this equation to get an expression for QP. So QP is equal to delta U plus P delta V. And basically the way we interpret this equation is that most of the thermal energy is released as heat. That's a QP part right here. But some work is done to expand the system against the surroundings. And that's where the P delta V part comes from, all right? And the example I was pointing to here in the next slide is the reaction between magnesium and hydrogen, and hydrochloric acid to form hydrogen. And in this particular case, it's an exothermic reaction. And some of the energy change results in the gas hydrogen being pushed out against atmospheres. And delta U, of course, would be the change in internal energy of the system. So I was saying here that this is the equation that is used to measure or calculate the heat change under constant pressure conditions. Okay, as stated here, most reactions occur under constant pressure conditions. So basically the heat change evolved would be equal to what we call the enthalpy change, all right? And this is the equation for enthalpy. So basically enthalpy is the heat change under constant pressure conditions when it comes to these types of reactions undergoing changes under those conditions. Okay, so let's talk about enthalpy. We'll be talking a lot about enthalpy pretty much for the rest of this chapter. What time is it, by the way? 1:27, okay. Okay, so let's talk about enthalpy, the different properties of enthalpy. First thing we're going to say here is that enthalpy is an extensive property. What does that mean? It means that the amount of enthalpy change is dependent on the amount of substances that are present in a reaction. And you see here in this little green box, it says 2 logs on a fire gives off twice as much heat as does 1 log. Now, of course, we're assuming that all the logs are of the same size exactly, which is very unlikely. But the point here is that, you know, the amount of substances involved will affect quantitatively and proportionally the amount of heat change that is occurring, all right, for this process. Another thing that we need to talk about is the fact that because enthalpy is dependent on these state functions, namely U, P, and V, that means that enthalpy also will be a state function as well. And therefore, everything that we said about state functions earlier will apply to enthalpy changes, right? Enthalpy changes have unique values, right? Delta H, right? And the enthalpy change depends only on the initial and final states, which come as no surprise because it's a state function. Okay, so let's talk about the measurement of enthalpy changes, right? Firstly, enthalpy changes are measured experimentally for the most part. We can actually do calculations of enthalpy as well, but that would be dependent also on experimentally determined values. If the values of enthalpy is negative, that means that the reaction is exothermic. If delta H is positive, that means the reaction is endothermic. So for example, what we see here are what we call energy diagrams, or more specifically, enthalpy diagrams. The one to the left is an example of an exothermic reaction where you have the reactants of a higher enthalpy compared to the products. So therefore, as you go from reactants to products, there will be a decrease in enthalpy. In fact, pretty much the change in enthalpy would be equal to the total enthalpy of the products minus the total enthalpy of the reactants. All right, so it's always products minus reactants. So if the enthalpy of the products is lower compared to that of the reactants, then the enthalpy change will be negative, which means that the reaction is exothermic. And then on the right side, we have what happens in the case of an endothermic reaction, where the enthalpy of the products is greater than the enthalpy of reactants. So again, if we follow this formula, we see that delta H is positive for the endothermic reactions, all right? Okay, all right. So let's talk about what happens if the reaction is reversed. Well, very simple. As far as delta H is concerned, the sign changes, right? So if the reaction is exothermic going in one direction, then the reverse reaction will be endothermic, all right? Therefore, if you have a cyclic process where you go from A to B and then from B back to A, that means that the total enthalpy change in that process would be 0. And that is true for every cyclic process. So for example, let's look at this example right here. The reaction of mercury to oxide, when heated, it forms mercury and oxygen. The enthalpy change for that reaction here is shown to be equal to 90.83 kilojoules. So if you were to do the reverse, then the enthalpy change would be minus 90.83 kilojoules, right? And that is true for every reaction without any exception, right? Whatever the enthalpy change going in one direction, the enthalpy change going in the other direction would be negative. Same quantity, but negative. All right. Okay, so based on what we have just covered, let's look at this question or these examples. So the first question says, given this equation. So we're given this equation and we're given this enthalpy change. Then the question says you have to calculate delta H for this equation. All right. So my question to you is this. Compare these two equations together, right? What is the difference between these two? And let me say that by way of giving you a hint, I'm looking for two things. There are two differences between this equation and this equation. All right. And again, for you guys out there in Zoom, you can also participate by answering this question. You can type something in the chat, or if you want to say something, I have no problem with that. But there are two differences between this equation and this equation. What are they? Well, okay, so you're saying what? The coefficients, right? For H2 and I2 is half and half, and this is 1 and 1, right? But there's also a change here, right? You have a 2 here, and you have a 1 here. So what can you say generally in terms of what you just pointed out? Is that the coefficients for the respective substances would be half of what they were here. All right. So that's one difference, one important difference. But there's another difference between these two equations. Can anybody tell me what that other difference is? There's another important difference between those two equations. Okay, so one person says the first equation is a synthesis reaction and the second one is a decomposition reaction. Okay, I wasn't thinking about it in that light, but you're right. You're actually right. But the answer I was looking for is the fact that the product of the first reaction is a reactant of the second reaction and vice versa, right? So basically, not only are the coefficients halved, but the equation is flipped, right? Those changes will affect the delta H value that you're trying to calculate for this reaction here, right? So basically, to get the delta H value here, exactly. So the delta H value here would be equal to, because the reaction is flipped, the sign is going to change, right? So you're going to have minus 52.96 kilojoules. And because all these coefficients are halved, to get the corresponding coefficients over here, you're going to divide that by 2. So whatever that gives, that would be the answer. So in this case, it's 52.96 minus divided by 2. So the answer here will be equal to 26.48 minus 26.48 kilojoules. All right, and that's it. All right. Okay, and this will become important later on when it comes to other problem-solving exercises that we're going to meet later on. Okay, so that's the first example. Now, the second example says the complete combustion of liquid octane, and it gives you the formula, to produce gaseous carbon dioxide and liquid water at 25 degrees Celsius and at a constant pressure gives off, and let me underscore this right here because that's important. Let me underline it here. gives off 47.9 kilojoules of heat per gram of octane. In fact, this line here is important, right? So the question is asking for you to write down a chemical equation for this, representing this information. Now, what this actually means, what they're asking for is for you to write down something like this, right? In other words, not only the equation for the reaction, but what the delta H value is going to be, all right? So how do we do this? Well, the first thing we need to do is what? Okay, so what would be the reactants in this equation? In fact, you know what, let me do this, because I'm going to need some space here. Let me see if I can. And let me try Word this time. Okay, so that's a question. And then, okay, so the question, this is the question. So as you correctly said, we need to write the equation. So what's the equation for this reaction right here? Okay, so that's C8H18L liquid plus, remember it's combustion. So what always happens in combustion? Well, carbon dioxide will be produced. In fact, let me put that over here. Right, but what will the octane react with? Anybody? What happens always in a combustion reaction? Okay, two persons are. Okay, one person says it reacts with water. No, water would be a product. Another person's said react with oxygen, and you are correct. So O2. And then what's the other product? Water. Exactly, water. Okay, very good. And then what do we need to do after that? And by the way, it says liquid water. So I'm going to put that here. And oxygen, of course, is a gas. And then what do we do after that? We balance it. So how do we balance it? Okay, so what do we do? To balance this equation. Well, this should be easy for you guys by now. Let's balance the carbons. How would we balance the 8 carbons over here? Or hold on, somebody was saying something. Oh, somebody's actually giving you all their numbers. And I think she's right, 2, 25, 16, and 18. 2, 25, 16, and 18. And I think that is indeed, just checking here. Yep, that's correct. Okay, so that's the first thing we need to do, all right? Okay, so the other part is finding out what delta H is. So this is where the more quantitative stuff comes in. So basically, it's based on this information right here. right? The amount of heat that is given off, right? So what is delta H going to be equal to? Well, that would be equal to minus 47.9 kilojoules, because the question says that the heat is given off, right? If heat is lost by the system, the heat change is negative, so that's why we put minus here, right? Per gram of octane. So what we're going to put here is gram of octane, which is C8H18. But remember, these numbers here represent moles, right? So what we have to do is convert from grams to moles. So we're going to put the molar mass. We need the molar mass of octane. So 1 mole of octane will go down here. And the molar mass. And again, I'm going to cheat a bit. I'm going to what's up with this thing? I'm going to use the molar mass calculator. Excuse me. Oh man, time's almost up. Okay, let me do this quickly. C8H18. And according to this, it's 114.23. So let me go back here. What am I doing? 114 point. What did I say? 114 point. Okay. So I'm going to put that number up here. 114.23 grams of C8H18. And then so that represents, okay, so this will cancel out with that. And what I'm going to do next is simply multiply by 2 moles of C8H18. And the reason why is because of this coefficient of 2 right here. So let's see what that gives. Where's my calculator? So that would be minus 47.9 times 114.23. And then I multiply by 2. So round off to 3 sig figs. And the answer I got is 1.09 times 10 to the 4 kilojoules. And that's it. Oh, minus, don't forget, minus. Because the reaction is exothermic. All right. Okay, so that's basically how that is done. Any questions in the last minute that we have left? So no questions. That's pretty much it. Now, let me remind you that assignment number 5 is due tomorrow. So make sure you complete that. If you have any questions while doing it, please let me know. I'll be here in my office from 2 to 5, and I'll be online tomorrow from 2 to 5 as well. All right. Okay, so that's it for today. I'll see you guys next Tuesday. Oh, somebody has a question? Oh, okay. Yes, Miss Bartram, I will do that right now since you said so. I'm going to open up a Dropbox for assignment number 5. So let me go here. Okay, assignment number 5. And I'm going to make that due tomorrow, which is the 13th. And let me make sure that the Dropbox is open. Okay, yes, it is. Okay, so now you can submit it, all right? All right, folks, so I'll see you guys on Tuesday. All right, take care.